In this tutorial, we're going to be looking at something called Boolean logic. Boolean logic is a way that Grasshopper uses, and actually many programming languages use, to represent true or false values, which are basically like yes or no statements. So we use Booleans to do things like test a piece of geometry and do one thing if the value is true and another thing if the value is false. So let's take a look at this in practice. So what I'm going to do is I'm going to create some geometry in Rhino that we can test. So if you haven't watched the tutorial on referencing geometry from Rhino, some of this might be new to you. What I'm going to do is draw some rectangles. And I'm just going to draw some little ones and some big ones. And you can follow along with this if you would like. And what I want to do is take this entire list of rectangles and do something different to the small ones than the large ones. So how do we do this? Let's actually use the geometry pipeline we saw last time to automatically load geometry in from layer 02, which is the layer I'm on now. So we're going to grab the geometry pipeline from Param's geometry pipeline. And we're going to say, grab me everything from layer 02 that is of type curve. And now you can see that this gets referenced in. So what we want to do is split this list so that we do one thing to the small rectangles and another thing to the large ones. So that's going to take a couple steps, but this is a very common pattern in Grasshopper. So first, we need to know which ones are small and which ones are big. And for now, let's use area as the kind of guideline. So I'm going to just, as a guess, I'm going to look at this and say area equals 0.36. And the big ones are like 4. So if I get the area of these curves, I'm getting out a list of curves. And if I take the area, which as I found out lives under surface analysis area, I can see the range of areas I'm getting. I'm getting a list of areas, one for each curve. And what I want to do is say, if the area is larger than 1, let's treat it as a big curve. And if it's smaller than 1, treat it as a small curve. And then we'll decide what to do with the small ones and the large ones. So here's what we'll do. We want to test this number. So usually it's easy in kind of spoken language to just say, do this thing to the ones that are big. But in Grasshopper, we're going to have to break that up into a few steps. One of those is figuring out their size, which in this case is the area. The second thing is testing that size to figure out if it's greater or smaller than some threshold. And then the third thing is actually separating out the list according to that result. And then the fourth thing is actually doing something based on that. So we're going to see all of those steps. So we've done the first one already, which is we've measured the area or the size. Then we're going to want to test this area. So we're going to use some mathematical operations to do this. Under math operators, we can do things like larger than, smaller than, equal to, or almost equal to is how to think of similarity. So if we only wanted the rectangles that had an area that was almost 4, then we could do that with something like similarity. But in this case, we just want all the ones that are larger than, and then we're going to specify larger than what. So this is going to give us back a result that is going to be true if A, the value in A, is larger than the value in B, and it will be false if that is not true. So the area is the thing we want to test. The question we're asking is the area larger than some value, which is going to be our threshold? So this is like a Mad Libs that says, is blank larger than other blank, where blank 1 is A and the second one is B. So this is what we're filling into the first part of that. And then the second part is whatever we want that threshold to be. So I'm going to create a slider. Let's just leave it like this and set it to 1 for now. We might want to tweak this slider a little later. And we will see, if I copy and paste this panel and plug it into the results of the test, that it's giving us back these true or false values. False, 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 false. These are all smaller than 1. This one's larger than 1. This one's larger than 1. This one's smaller than 1. False. So we can use these lists of Boolean values, the results of some test, to apply things what we call conditionally. So do one thing if it's true and do a different thing if it's false. There are a few different patterns for doing this, but I think by far the most common one is using a component called dispatch. So dispatch, which I will search for, it lives in the set components under list, takes a list of data, the list to filter, and a dispatch pattern also as a list. And you can see that by default, it actually has this pattern of true, false. And I think what dispatch does is it'll repeat that pattern over and over again if you have too many items in the list. So, but usually we actually want to generate that list, and that's what we've done here. So we could take all of the areas and all of the test results, these Boolean values, and this would create a new set of lists. One list in A, which are going to be all of the values where true was present, so all of the values that are larger than 1, and all of the values that are smaller than 1. And this is useful, but really we don't actually care about the areas. We just want to use the areas as the basis of the test. So in fact, we want the curves where the area was larger than 1. So in this case, the L, the list that we want to dispatch, is actually not the area itself. It's the geometry that we pulled in. And we can do this because we have 12 of these curves and 12 area values. So this also adheres to the rule I've spoken about before of always wanting, if you have multiple lists going into a component, either n items, so in this case 12, or 1. So in this case we have 12 curves, 12 Boolean values, and we're getting back now a split list where we've got the 7 curves that are smaller and the however many 5 curves that are larger. So what's something we could do? We could create planar surfaces through the large ones. So we'll go to surface, freeform boundary surface, which will take any list of planar curves and try and find surfaces between them. And this is a good way to just kind of visually indicate which ones are big and which ones are small. And maybe for the other ones, we'll create dashed lines. And we can do that under curve division dash pattern. So I'll take these curves and I'll supply a dash pattern. This works the same way as like in Illustrator or something. And so I'm just going to create a slider at, this is the shortcut where you just type a number in the search field to create a slider, and we'll make that our dash length. Hard to see because a lot of other things are visible, but if I turn off the preview here, you can sort of see. Maybe this was a bad example, but if I hide all of these, I've now got dashed lines for the small ones. Maybe I'll make my dashes a little smaller. So one thing we can do is actually adjust the threshold. We can say, actually, we want to treat these, the kind of medium-sized ones, as bigs and leave the other ones as small. Or maybe we want to use a different basis for the test. Maybe we want to care about the y dimension, but not about the x dimension. So maybe we don't want to use area. A quick way to get a dimension off of an arbitrary object, because remember, there's nothing that says that these have to be rectangles. In fact, if I, we'll hide my title text. If I draw another curve over here that is not a rectangle, then we can't say rely on it having a certain number of edges. So what I often do is take any geometry that I'm trying to process or run a test on and take a bounding box from it. So let's look at what that looks like. If I double click and type bounding box, it's going to take any geometry that I supply and create a box. Actually, it's generally a 3D box, although it might be flat as it is in this case, that encompasses that geometry. So because we've already got rectangles, we're getting those rectangular boxes. And so it doesn't look like much has changed. But for non-rectangular geometry, it's a way to get something that's like predictable, that's very easy to work with. So now let's find the dimension. Let's find the x dimension of each of these things. So to do that, we can use deconstruct box. So you'll notice that a lot of components in Grasshopper have this kind of construct and deconstruct pattern where there's a way to sort of make a thing and then there's a way to get the component parts back out of that thing. And this is a good pattern like that. So bounding box, we're going to use deconstruct box, which also lives under surface. So all of the box related stuff lives under surface. Deconstruct box, box properties, evaluate box, box corners, that kind of thing. So this is going to give me back not actually the dimensions of the box, but the domains of the box. So if this box is located at x equals negative 3.7, and on this side it's negative 0.7, then the x value I get back from deconstruct box is the domain from negative 3.7 to 0.7. So what I don't really care about that, I just care about the length. And a nice shortcut is that if you pass a domain through a number parameter, you can force it to become a number. So if we go to params, primitive number, let's just look at the data as we're doing this. If I plug this in, you can see I've got both ends of each domain represented, but I don't really care about their physical position. I just care about their length, which I can get by plugging into a number. Now this will actually tell me how wide is each box. So now I can use that as the input value to my test. Is the width larger than this value? I'm going to turn off preview here so we can use our split. And now this is going to be a width threshold. So anything that's wider than my slider value will get surface filled in, and everything that's not as wide will go the other way. So we could switch this out and use the height by replacing our x value with a y value. And so now these are all going to count. And so you can start to build up more and more sophisticated tests. We could do a test that says, like, is this a circle, or is this a polyline or not? One way we do this, there are a few ways we might do this, but one way is to rely on the fact that when this comes through a text panel, it actually becomes a piece of text, which is the words referenced circular curve. So one thing we can do is test whether or not those are the words that we got. If I add another circle here, just so we have something interesting. Now we have a few more circular curves in our list, and I'll add, one more rectangle. So one thing we can do is actually type that value, referenced circular curve. And you might think that you could do an equality test here. You might think that you could use the same sort of operation where we say, is this equal to that? But equals doesn't really like text. It turns red. It says data conversion failed. Equals really expects a number. So instead, we use a different kind of test, which is a text match. Match text is the component. This lives under set and text. There's a whole bunch of text-based operations over here. And so we can say, this is the pattern that I want to match. Is it referenced circular curve? This is the thing that I'm testing, which is the text representation of this geometry. And just like we got from our greater than test, we're going to get back a list of Boolean values. It's going to be true where it's a circular curve and false where it's not. So now we can use this. I'm just going to tidy this up a little bit. We can use this value to be our Boolean value. So I'm going to feed that in to be our dispatch pattern. And now it's going to fill in all the circles and ignore all the non-circles. It's going to make dashed lines out of them. So you can start to get more and more sophisticated about this. You can combine tests. So, you can say, give me things that are larger than this value. So this is our old test. But that are not circles. So we could say, if it's larger than this and a circle, use that. So in addition to just sort of running a single test, you can combine the results of tests using operators like and, or not. And we'll look at these here in a second. And says, take two lists of true and false values, and return a true only if both of the inputs were true. So if it was larger than 1 and a circle, color it in. In this case, all of the circles were already larger than that. If I had a really small circle, it would get excluded. We can also say large ones that are, so ones that are larger than 1 and not circles. And the way that we test that is to invert or pass through a not gate on the test that we want to be not true. So in this case, it's going to be larger than is true and text match is not true. So we're going to use this other operator called a not, which all it does is it takes trues and makes them falses and falses and makes them trues. And so if we do and not, we can build up even more complex logic. This is all of the large curves that are not circles. And so with this sort of a pattern, you can dynamically apply logic to geometry that you've generated or geometry that you've drawn in Rhino and follow increasingly complex rules about how to handle or process that geometry. So it's really a powerful concept.